I'm the co-founder of Fuzzland, and I'm a PhD student at UC Berkeley. I'm going to talk about how we mitigate smart contract attacks in the real world. So as you may or may not know, smart contract attacks in this year has already led to more than $100 million loss. And some notable cases are Wuland, which led to 21 million loss, and the Ronin Bridge incident happened yesterday, which has been stolen more than $12 million. So there are different measures to stop the attacks. Some people refer to traditional audits, which they ask the auditors to go over the smart contract code and see whether there are vulnerabilities. But there are still some issues with auditing because auditors can miss issues. For example, Parallel Finance got hacked for 5 times, although they got audited for 11 times. There's also other issues on chain, like the protocol could be incorrectly deployed, incorrectly configured. For example, like Wuland, it's misconfigured and finally led to more than 20 million loss. And people also refer to other on-chain solutions to stop the attack. One of the most well-known solutions is to conduct attack front-running. So I guess you may have heard of Coffee Babe and Blockstack saving millions of dollars in the past by front-running the attack. So what is attack front-running? Attack front-running is basically cloning the attacker's exploit while they're still in the mempool. When we see the attack transaction from the attacker, we try to reconstruct another attack so that we can receive the stolen funds instead of the attacker, and we insert that our transaction in front of the attacker's transaction so that we can be the first one who hacked the protocol rather than the attacker so that we could rescue the funds. So it sounds really easy to build the front-running bots, and it's basically just cloning the exploit and trying to get it onto the block first. But how effective it is today. So we did a statistic for attack front-running in 2024, and this is the number we got. So attack front-running bots actually rescued $0 since January 2024 in 0 incidents. So you may wonder, like, what is the root cause of this? Is it because attackers using funky methods to bypass the attack front-running bot? And this is the reason we got by analyzing the past blockchain data. We see that 99.1% attacks are actually sent to the private RPCs or happens on the chain without mempool. So this means that no one can see the transaction before they got mined on that chain. And this also means that attack front-running bots cannot see those transactions, and they cannot insert additional transaction before that attack transaction because the attack transaction is already mined. So overall, front-running bots cannot do anything when this happens, as it's already too late. And you may also wonder what happened to that 0.9% of the attacks. And the reason is competition. So because front-running bots is really easy to build, not just white hats are building the front-running bots. Malicious actors are also building front-running bots. And their front-running bots sometimes are way more effective than the white hat's bot. And they could steal those funds and never return the funds. Additionally, we also see that there are a lot of competitions between the bots, which leads to majority of the funds being burnt as gas fee. So we did a small experiment to show that how this happens. We actually sent a bait transaction last year on Binance Smart Chain to extract more than $3,000 in a vulnerable contract we deployed. And as soon as that transaction gets to the mempool, we see more than 10 front-running bots start to do the front-running, and they start to increase the gas fee over time so that they could be the first one who mine their transaction and be the successful one. And surely, like after 600 milliseconds, we do see that the gas fee has already increased to $2,500, leaving them only $500 profit from running this transaction. And finally, only one bot could succeed, and that bot could only receive less than $500. So it sounds like attack front running is no longer an effective method to stop the attack, but we do have some insights. So attackers does not conduct the attack atomically most of the times. They always conduct some pre-work before the attacks. For example, let's take a hedge finance exploit as an example. The attacker deployed the smart contract, which is the exploit for launching the attack a few minutes before they really launching the attack. So there's actually a lot of information in that exploit contract, and if we can find a way to derive the attack from that exploit contract, then we could actually have plenty of time to do the front running, or we can hijack the attack. And another thing we observe is that attackers today are not very smart. Sometimes they leave some funds behind and they need to use multiple attacks to drain all the funds. This happens in the cases like LeFi hack, which the initial attack only drained less than $2 million, while the total hack drain led to more than $11 million loss. And there's also cases like hackers stole the funds from the protocol deployed on one chain, and there are other deployments on other chains. For example, KyberSwap is a DEX that is deployed on multiple chains. The attacker first hacked the KyberSwap protocol on base chain and drained less than $200K, while the subsequent attack on different chains finally drained more than $46 million. And there's also additional copycat attacks happening on the protocol's fork on different chains days after, where the copycat attackers manually analyze the exploit and derive their new exploit for other protocols. So what if so based on these two observations, we could actually get two insights. So the first thing is that we can actually hijack the attack, because if we can see a lot of information before the attack really happens, then we can figure out some kinds of model or some kind of prediction stuff that could generate an attack transaction based on just those pre-works. And another thing is that we can background the initial attack. When we see the initial attack, we already know how to do the attack for that protocol. And we just need to do some tweaking so that it could be applied to other victims that have similar traits. So let's first do a statistic understanding of how effective this is. So suppose we have a mysterious oracle that could automatically turn the initial attack into the attack that could drain all the funds from the victims. Then we could actually rescue 57% of the funds that are stolen since January 2023. And if we have another mysterious oracle or a mysterious box that could convert some pre-works into the attack transaction, then we could rescue more than 26% of the funds that are stolen since 2023. And but like, how can we construct this mysterious oracle? And this is our way of constructing it. I will give a high-level overview, but there could be other ways doing this. So for attack hijacking, what we can see is some pre-works. And to simplify the things here, we just limit our scope to the exploit contract deployments. So as soon as we see the exploit contract deployment, we can do some decompilations and figure out all the things that we can call on this exploit contract. For example, in the Onyx protocol, this is the code that the attacker used to launch the attack. This contract is deployed a few minutes before the real attack happens, and what we can see is that there are some functions, and this specific functions has two parameters. And if we can correctly figure out these two parameters, then we could actually derive the attack transaction that the attacker will send. But how can we find this argument? This actually got turned down into a program repair problem, which we could leverage our experiences on program repair techniques developed in the last 3 decades. But I'll share like the simplest method to do the program repair. So we could simply just try all the values for these two parameters and see whether we could gain the profit. And as soon as we see that we could derive two parameters that could lead to profit, we could use binary search or ternary search to optimize the profits so we could gain the maximum profit by executing this exploit. And another thing we do observe is that the attackers commonly have authentications in their exploit contract because they don't want other people to call their exploits or perform the attack on behalf of them. And for example, in the Onyx protocol, there are checks on message sender. There's also a check on hash of the transaction origin. And these kinds of checks are actually really easy to bypass if we are trying to find out the attack transaction. We could simply remove all the requires in the exploit contract, because all the requires in the exploit contract is not going to do any work. They are simply just for checking validity of something or checking whether you're really the caller, you're really the owner of this smart contract. And by rewriting the program with some heuristics, or by rewriting the exploit contract with some heuristics, we could actually derive a exploit contract that has no authentication and no validity check. And with this, and plus the parameter brute forcing method I described before, we could derive and attack transactions that the attacker will send. And for attack backgrounding, the task changed, so we no longer need to derive the parameters. Instead here, we want to find the new victims based on the initial attack. And as we can see the initial attack, we do see what is the relation between the victims and the contract that are interacted by the exploit. I'll use Paraswap attack as an example. So in this attack, the attacker drained all the funds approved to the Paraswap vulnerable contract. And if we want to find new victims, we simply just need to, as we can see that their relationship is that the victim approved tokens to the Paraswap contract, we could simply do a search in the indexer to see who else conducted the approval to the vulnerable contract, and by replacing the victims, replacing those addresses in the exploit, we can generate a new exploit that hacks the new victims. But still, there are issues with this simple strategy because, for example, in Paraswap, different users approve different amounts of tokens to the vulnerable contracts. So we also need to try to fix the exploit if it fails. And to fix it, get back to the parameter brute forcing part. We could still use the program repair strategies, and for here, we actually use different kinds of methods, including fuzzing, symbolic execution, and so on, to instantly figure out those values. And so we implemented our strategy in a few thousand lines of Rust, and we did some backtesting, and this is what we see. If we deploy our solutions since January 2023, then we could actually rescue more than $120 million from attacks. We could actually rescue 20% more than those stolen by the initial attacks. This is because we could find the more optimized parameters for the exploit than the attackers. And for backgrounding backtest, we found that our solution could rescue more than 94% of the funds stolen in the subsequent attacks. And we also deployed our solution in real world, and our solution has already rescued $50 million since March. We have conducted hijacking for some swap protocols, and backgrounding for some swap protocols, and still all the funds that are approved, that are still vulnerable. And we also did some hijacking for landing protocols like Teller v2. Additional thing I want to mention is that we also did backgrounding for Sony Finance, but it's a bit different. Our solution could only generate another exploit that could drain the funds, but the funds are sent to the attacker, not to us. And with this exploit, we quickly identify what is the issue with the what is going on there. And we finally, with some manual intervention, we could derive a new exploit that could stop the attack. And we finally rescued $6.8 million in this case. All right, so this is all about my talk. And thanks to our collaborators. And thanks for listening. Yeah.
Yeah, nice presentation. I was wondering if you have seen any adaptation on the attacker's side, meaning that instead of launching a two-phase attack, they would just attempt to drain all the funds in the first phase.
Yeah, there are actually a lot more this type of attack happening recently. The attacker simply use constructor to launch the attack so that they could launch an attack atomically. There is no pre-work, there is nothing else required. And I guess this is due to the trying to adapt to our strategy, which is also currently used by some other bots.
All right, thank you.
Yeah.